Okay, students, this is lecture number 5C. I've just tried to make them in some small parts, these lectures, because these are very informative lectures from the theory point of view, and they are talking about a lot about the harmonics. And if you remember the last lecture, we separated the space harmonics into two types of harmonics, and I told you at that time that if the harmonics are 6m minus 1 and the harmonics are 6m plus 1, these are two different types of harmonics which are going to be present in the space harmonics, and if you change that value of m from 1, 2, 3 and so on, so if this was m was going to be changed to 1, 2 and 3, this was the fifth harmonic, this was the seventh harmonic, this one was the 11th harmonic, and this one was the 13th harmonic, and so on. You can complete this table lot. Now, today we are actually going to talk about that how this is going to have the effect on our machine, and what sort of speeds we are going to get from this harmonics over there, which are actually fifth harmonic, the seventh harmonic, and all that stuff over there. Now, since these all harmonics have actually come from the space harmonics, and we talked about in the very previous first lecture of this 5A series that all these harmonics are going to be caused because of that stepped sine wave which is actually being created over there. So if I'm talking about this step sine waves over there, so let me just draw one sine wave, step sine wave, and I hope this is the simple step sine wave, and you can make this step sine wave a little bit more elaborative. So I have made it. In fact, I can please answer me on this one, that how many, what is the value of g for this type of a waveform. So this is actually the mmf waveform which is being created inside the air cap over there. Now this is a step structure. Certainly it's going to have some fundamental, and it's going to have some harmonics inside it. So one question which I'm leaving with you over here: if this is the step waveform in front of you for the MMF for a three-phase machine, can you tell me what is the value of G in this machine, so that this is giving you this step structure over here? Please answer me in the comment section. Maybe in the next video I can give an answer that your answer is correct or wrong. So this is the MMF waveform, and in the very first part we talked about that this is going to have harmonics, it's going to have the fundamental, and it's going to have the uh, third harmonic or the odd harmonics, all are going to be present, but we proved it that the odd harmonics are not going to be present. Why? Because they are going to be having that distribution factor equal to 0, not every time, but always whenever there is going to be a phase spread equal to 120 degrees over there. We will come on to that one when we will discussing the windings in much detail, that why this is going to be 0 every time and all that. Now since this is an MMF waveform, and since I am interested in more in the fundamental over here, and since over here on the x-axis I have the alpha angle or the space angle over here, so this is again the space angle over there. So when I'm trying to draw the fundamental waveform of the MMF is certainly going to be a sinusoidal waveform. So this is going to be something like this, and if I draw the other side of that one, so this is going to be the fundamental waveform. And certainly depending upon whatever that structure is, this is not angle, this is not time t on the x-axis. Please remember, this is the space angle alpha over there. So certainly based on some assumption I can take it this is the north pole and this is the south pole created inside the whole 360 degrees. This is the whole 360 degrees from 0 to 360 degrees inside your machine. So you have two poles being created over here. Now after the fundamental, since the third harmonic can also be present, but yes, that can be cancelled out in some cases over there, but let me just keep that in the same way that you are going to have the third harmonic over there. So the third harmonic, if I draw that one over here, and this is your the middle line, that is 180 degrees over here. Now for the third harmonic, so just like the fundamental, if this is the third harmonic over here in front of you, this means that they are going to be the multiples of this, the fundamental, that is actually the third multiple of this one. So if I draw this one, maybe supposing with another color over here, so let me just make it into some equal parts over here, so the waveform is actually much better. So the third harmonic is going to be something like this, and then we go in the other one. So this is like this, and since it's going to be a third harmonic, it's actually the multiple, three-third multiple over here. So this is going to create a north pole, this is going to south pole, this is again going to create a north pole, this is going to create a south pole, this is going to create a north pole, this is going to create a south pole. Now what this is telling you, that there are now going to be 6 poles created for the third harmonic over there. So and if I repeat the same thing for the fifth harmonic over here, so when the fifth harmonic is going to be plotted over here, so it's going to be producing 10 poles over there. So what is happening, I'm not going to draw this one because it's a little difficult over here. So what you are seeing over here is this, that from the fundamental, if this fundamental number of poles were actually being considered, from the fundamental you were having number of poles equal to 2. But when you had a third harmonic over there, the number of poles became equal to 2 multiplied by 3, where 3 is actually the multiple, so this is actually equal to 6. And if you are talking about the fifth harmonic, so this is going to be equal to 10 over here. Now this is very important over here, that by increasing the harmonic number, the number of poles which you are creating. Now the important point over here is this, that when the poles are increased, how is the speed of those harmonics changing? Now I'm not concerned with the speed of those harmonics, I am concerned with the magnetic field that is being created because of those space harmonics over there. So what I am more concerned over here is this, since the I'm just still in the stator or in the air gap at present, I have not just gone towards the rotor and there is no induced EMF still taking place. I'm not talking about that stuff over here. This is just the stator induced magnetic fields which are revolving, and since the MMF waveform is not a pure sinusoidal as shown over here, it is having some G value over here, and because of that it has a fundamental which has certainly going to be producing 2 poles. This is the smallest pole. Now if this MMF was changing by maybe like 4 times in the whole 360 degrees, then certainly this would have been a 4-pole machine, and then every time when it was a third harmonic or a fifth harmonic or a seventh harmonic, you will be multiplying 3 and 5 and 7 by 4 over there, because 4 was the actual number of poles in that fundamental. Now the next thing very importantly over here is it, that if NS, you all are familiar with this formula, that Ns is equal to 120 F by P, and since over here in this formula, this F is the electrical frequency. This is very important. This is the electrical frequency. This is not the frequency of any speed or anything being induced over there. This is the electrical frequency being given from the supply. So this is constant. So this Fe is constant in any case. So it's not changing, it's given from the supply source, from the WAPDA, it's not changing, so the electrical frequency is the very same over there. Now, if you're talking about the fundamental, since I'm just going to write NS1 over there, so it has a speed equal to 120 F electrical, and here I have just the generic formula P over there, so this is not going to change over there. So this is for the speed for the fundamental. Now, the same formula, when I am going to write it down for the third harmonic over there, this is going to be equal to 120 times Fe, and this time the number of poles are not going to be P, they are going to be 3 times that of the P. Now this is 3 times that of the P, so I can write this one also as, because this portion over here is equal to Ns. So I can write this one as Ns1 divided by 3. So this means that the third harmonic, this is the third harmonic, so the third harmonic is going to create a revolving magnetic field, and it's going to create 6 poles if I'm talking about the fundamental having 2 poles. So here there is going to be 6 poles over there, or I can call it the number of poles are going to be 3p if p is the generic number over there, but the speed of that is going to be smaller. It's going to be ns by 3 over there. And if I do the very same for the ns5 over there, without writing this one over there, so this is going to be ns1 divided by 5, so this is going to be the fifth harmonic over there. And if I'm interested in ns7 over there, this is going to be ns1 divided by 7. So this is going to be the 7th harmonic speed over there. So what is happening over here, as I'm increasing the number of harmonic or the nth order of that harmonic, the speeds are also decreasing. So what is happening, that not just the MMF waveform is actually having more number of poles when it is being bifurcated into its harmonics and the fundamental. I am also having that the speeds of this harmonics, or the poles which are going to rotate over there in the space over there, they are also rotating with a smaller speed over there. And their speeds, generically, if I am interested in the nth order harmonic speed, that is going to be equal to ns by n. So this is actually the nth order harmonic speed over there. So if I want to actually want to find out the speed of that nth order harmonic, that will be equal to ns by n. Yes, one thing very important over there, it is revolving in which direction, that is going to be decided by that equation, that is 6m minus 1 or 6m plus 1. We have already talked about this in the previous lecture, that 6m minus 1 is certainly going to be producing those revolving speeds or those revolving magnetic fields. Those harmonics are going to produce which are revolving in the opposite direction, which is actually the 5th harmonic. And if this is moving in the 7th harmonic, or the next one, that is actually the 13th harmonic, so they are going in the positive direction over here. Okay, now after this nth order harmonic, since now the nth order harmonics are bifurcated into two types of harmonics, one is called as 6m minus 1, the other one is called as 6m plus 1 harmonic. So we have to generalize this one because they both have actually a different direction over there. So if I am talking about the harmonic, so the speed of 6m minus 1 harmonic is going to be equal to ns divided by 6m minus 1, and the same formula for 6m plus 1 harmonic is going to be equal to ns over 6m plus 1. So what this is telling me, that if I am having, and certainly you can generalize over here because these are moving in the opposite direction, we have proven it previously also, and they are moving in the same direction as the fundamental. So ns divided by 6m minus 1 is the speed of the 6m minus 1 harmonic, which is actually the first column over here which I drew in front of you. And if it is 6m plus 1, they are moving with the speed ns over 6m plus 1, where ns is actually the speed of the fundamental or the supply frequency which you are actually using it for the first case. Okay, now after this one, very important thing over here is this, that what is the relative speed over here. So the relative speed, so the relative speed of 6m minus 1 harmonic with respect to the fundamental. Now this is very important. Now what I mean by this? We know, supposedly, I'm taking an example that I have the fundamental going with ns speed. Now I know 6m minus 1, the harmonics, they are going to move in the opposite direction with respect to the fundamental. So I'm going to show them. I'm just in the stator. I've not gone in the rotor yet. I'm just in the stator at present. So this vector is going to tell me, and the speed of this one is going to be ns divided by 6m minus 1. Now you can see these two directions are totally opposite, and if I want to find out the relative speed of 6m minus 1 harmonic over here, now since they both are moving in the opposite directions over here, if I want to find out the relative speed between these two, what I will have to do, I will have to actually add both of these over here. So this is very important, and I hope you understand it, because if they were moving in the same direction, then I would be actually subtracting them. Okay, because they both will be having some speed difference over there, but here in this case they are actually moving in the opposite direction. So if I want to find out the relative speed of the 6m minus 1 harmonics or the other one way around, it has to be added together. So when I have this one, so this is ns, and if I open this bracket, this is 1 over 1 6m minus 1, and I can actually write it on even more. We can simplify this one. I can take this denominator, so this is 6m minus 1 plus 1, and this plus 1 and plus 1 are cancelled. So the relative speed vector is actually equal to ns into 6m over 6m minus 1. Now, so this is the actually the relative speed over here between the 6m minus 1 and the fundamental over here. Now, the same formula, without going into the proof of this, this is the relative speed of 6m plus 1 harmonics with respect to sorry about this one, with respect to the fundamental is, I'm not going to go in the proof, this is just going to be equal to ns into 6m over 6m plus 1. So this is the relative speed over here, and this is the relative speed for 6m minus 1. So these two are the relative speeds of the 6m plus 1 or 6m minus 1 harmonics with respect to the fundamental over here. Okay, now when you have got this harmonics over here, and so what now, these harmonics are present inside this stator MMF, and they are evolving with some speed. They have some number of poles. So now, because of these harmonics, there is going to be an induced EMF inside the rotor, and the rotor is also going to have the similar number of poles, just like the harmonics over there, and it is going to produce a torque with the help of this space harmonic. So now particularly over here, since up till now we have been taking an induction machine which was always working in the fundamental region, and by fundamental I mean that it was the first fundamental or the first harmonic over there, and it was producing that torque over there, and that torque was being produced in some certain direction and the machine was moving. But now, since there is space harmonics, and those space harmonics are composed of the fifth and the seventh, I have ignored the third harmonic because of that kV factor at present. So now, if I am talking about the fifth harmonic over here, and I am talking about the seventh harmonic also, because these are the first harmonics which are actually coming into play at present. So the fifth harmonic is going to produce a torque tau 5, and this is going to be opposite to actually the main torque which is actually going to be produced over there. And how this is going to be produced over there? This is going to be produced because of the stator revolving field which has the fifth harmonic over there, and then because of that there has been an induced EMF inside the rotor, that is also a fifth harmonic, and that is actually going to be also going opposite. So what is going to happen? Those two fields are actually going to interact with each other and going to give rise to those harmonic induction torques over there. And the seventh harmonic, this is almost going to be in the same direction, just like that tau. I can call this one as tau 1. Here this is tau 5 and tau 7. So what I mean by this one over here is this, that now instead of just the fundamental, there are also going to be two more torques, and these torques are going to be called as harmonic induction torques. So this is very important that these harmonic induction torques are going to do what on the torque slip curve over there. Okay, so these harmonic induction torques are going to be produced over here because of the fifth harmonic and the seventh harmonic, and I guess I don't need to tell that this fifth harmonic and seventh harmonic torques are going to be produced near ns by 7. Oh sorry, for the fifth one this is going to be actually ns by 5, and for the seventh harmonic this is going to be produced near ns by 7. Now what I mean by they are going to be produced near it, now if you remember your fundamental, that was actually the main induction machine before these harmonics were introduced, this torque was going to be produced near the speed ns, not exactly at ns but a little bit behind over there. For this purpose, if I go back on my main basic thing, that is actually a torque slip curve over here, and let me just draw this torque slip curve a little over here. So actually I was trying to actually, so if this was a torque slip curve, this was the induced torque inside your machine, this was the speed over here, and certainly this was going to have a speed 0. This was speed ns over there. You can have on the x-axis also the slip value. This is slip over here, or this is the speed over there. I hope everyone has an idea on this one. So this is the slip and this is going to be. So the torque slip curve, which was actually like this. And if you remember, this was a torque slip curve, this was the starting torque over there, this was the full out torque over there. Now, if I just zoom in over there, in this region, the working region of the machine was something like this region. This is the low slip region area of the machine, and in this region, the torque was being produced over there. Why the torque was being produced over here in this region? Because if you are going to have a load over there, and supposedly that load is having a load line, let me make that load line over here, and if that load line is somewhat like this over here. So if this is the load line, this is your load line over here. So at the point where it is crisscrossing this point, this is the point of your working of your machine. So this green color region was actually the working region of your machine, and this was the torque being produced over here from the fundamental. But now, because of that space harmonics, what has happened? You have now the fifth harmonic and the seventh harmonic. So the fifth harmonic is going to be actually produced near the speed ns by 5. Why? Because in the fundamental, this was the region the torque was produced, that was near ns. Now this time, the fifth harmonic, which is actually called as the harmonic induction torque, or it is also called as the asynchronous torque. This name is also given in some cases. So the fifth harmonic is going to be near ns by 5, and the seventh harmonic is going to be near ns by 7. Now what I mean by this? Now if I go back on this torque slip curve over here, and if I use another color over here, where the ns by 5 over here is actually moving in the opposite direction, and this is at ns by 5. But seventh harmonic, it is moving in the same direction, so the torque is going to be near ns by 7. Now if I plot on this particular torque slip curve, supposedly ns by 7 is the point over here at this point. Now what does this mean by this? Now when I'm talking about this ns by 7, this means that at particularly this ns by 7 speed, you are going to have another torque slip curve which is going to be like this. It's going to be very small. Why? Because the harmonics are not of that much value. But what is going to happen? This harmonic is going to be producing a small torque slip curve of its own, centered at ns by 7. Let me just rub this ns by 7 over here. So this is going to be the point of ns by 7 over here. So this torque slip curve is being created, and I hope I have not I have explained this previously also, that this is the motoring region of the machine, this is the generator region of the machine, and certainly if you can extend this beyond back, this is going to be the braking region of the machine over there. Now what has happened because of this seventh harmonic? The black color one, you can take this one as the fundamental. Now since the machine is going to be producing the very same, let me just rub this one a little over here. So a little, this is a little away from what I wanted. This is going to be just a little like this. I just wanted to actually be going down linearly over there. Now because of this ns by 7, and this is the first fundamental over there, I just made the static torque a little small over here. So what will happen when this first fundamental and the seventh harmonic, they both are going to be added together, and this is going to give rise to some added form over there. So that added form, when it is going to be added over there, since certainly in this motor region it's going to be on the higher side, so when the final resultant form is going to be added, it's going to be like this, and it's going to be added like this of a motor and a generator case over there. So what is happening over here, that if this let me take this a little far more. like this. So again, what has happened, I have added this black color, which was actually the first fundamental, and this was the seventh harmonic produced over there. So now what has happened, that the final waveform, which is actually this purple color over here, this is now also giving rise to this intersection at this load line. Now what does this mean? Previously, when the machine was not having any harmonics, the machine started from this particular point, that was the starting torque point, and it went through all of this and it passed through that over there, accelerated through it, and then it went at this point, because this was a stable point at which the machine could work very easily. This was the load line at which it was crisscrossing. Now what has happened, because the machine has now an extensive value of 7th harmonic torque, so this 7th harmonic torque, which is shown over here by the blue color one, and when it is added inside that one, this is now changed to a purple color waveform, and now the load line is crisscrossing at this point. Now this point may not be exactly ns by 7, but it will be closer to ns by 7, because the generator region can be a little bit changed shape over there. So what this means over here is this, that this point, when it is going to crisscross, it's going to give rise to a very stable point over here, and the machine, when it will be starting from the rest at this point, it will come at this point and will not accelerate further from this point and start moving at ns by 7 or closer to this speed. Now what has happened over here? We wanted the machine to go back to this point. Why? Because this was the actual operating point. We wanted the machine to run at ns speed. Now what has happened, that instead of going there, the 7th harmonic, which was producing a positive torque with a speed ns by 7, so there was a miniature torque slip curve created, and when we add that 7th and 1st harmonic, what happens? You have now a harmonic harmonic induction torque being produced, which is also an asynchronous torque. So the machine, when it is accelerating from this point over here down, it does not accelerate beyond this point, because this becomes a steady state point. The machine is steady at this point. But what has happened? This is now at a speed ns by 7. Previously, we wanted this to work at this point that was near to ns over there. This was a low slip region. Now, this is a high slip region, and if you want to find out the slip with respect to, because the machine is now working at ns by 7, and you want to find out the slip with respect to your revolving magnetic field, it will be enormous. Because if you remember your slip formula, the slip formula, let me just change the color because this is on the opposite side. So the slip formula, that was equal to ns minus nr divided by ns over there. What was nr? Nr was the speed of your rotor. Now what has happened? The speed of the rotor is not more than ns by 7, near to that. I'm not saying exactly ns by 7. It is depending upon the torque slip curve which is being created by the 7th harmonic over there. So what happened, when you plug in this value of nr at ns by 7, the slip comes out to be very, very large. Why? Because you can see the slip over here, it's increasing from this 0 to 0.21. So it will be something very, very large value. In terms of percentage, it will be also very large. In terms of percentage, you want to write this is from 0 to 100%. So what happens? The slip is very, very large at which the machine is operating. Now, it has two problems over there. The first problem, we wanted a speed near ns, so our load is not turning at that much. Yes, it is being provided with that torque that was required, but it is not working at that designated speed we wanted it to run. So this is the first problem. The second problem, if you remember your machine scores and the rotor copper losses were equal to S times your P air gap. This is very, very important. What was air gap? Air gap was that power which was traveling from the stator towards the rotor, and a part of that air gap power was converted into rotor copper losses, and the remaining went into mechanical power. Now what has happened, that since S is going to be very small, large, why? Because now NR is very, very small, so slip has gone to a very large value. So there is going to be a very huge increase in the rotor copper losses. So the machine is still pumping up with power, But what has happened? That power is being wasted as the rotor copper losses. So machine is still pumping that power, so it will have a considerable heating and the machine can damage itself. Now what we call this factor, this phenomena in which the seventh harmonic, which was actually in the positive direction producing a torque, but when the machine started from rest, this is only going to happen when the machine is going to start from rest. What happens over here? It intersects the load line at some point and the machine starts to work at that particular point, that is ns by 7 over here. So that ns by 7, the speed is very small and we call this factor or this phenomena as crawling. As the name suggests, crawling means that instead of working at the main particular speed we want it, it's now crawling. It's very slowly moving at a very strong speed that we did not want it to run. So this is called as crawling, and this is because of the seventh harmonic. That was actually because of the space harmonics being produced over there. So this concept is called as crawling over here. And as you can see, normally whenever we have been talking about the top slip curve, we have been calling it the saddle over there. Similarly, this is the saddle effect over here being produced, and when it is crossing at some point from the load line, then the machine gets running at a high slip region, and because of that high slip region, the rotor copper losses are increased considerably over there. I will just finish it off over here. I hope you can add the effect of the fifth harmonic, which is actually opposite, and certainly that will be sorry on this one. If I extend this one, and this is going to be going in the braking region. This is the braking region, and I hope everyone has an idea what is the braking region. This is the braking region, and braking region means that when the machine was running in some positive direction and you start doing some plugging. Plugging means that you change the phase sequence of any two wires and start to rotate in the reverse direction so that it is now going to brake on it. Now the fifth harmonic, which we already know from our previous discussion, that it is moving in the opposite direction. So it will be having a point. Let me just draw that point again over here. That will be at something ns by 5. So at ns by 5, you are going to have that top slip curve just like the seventh harmonic, like this. And when this top slip curve is going to be added on this one, this is again going to create a problem, because when the fundamental is going to be added with this fifth harmonic over here, it's going to again create that saddle effect and it's going to create a problem, but only in the braking region when you are going to do plugging. I will talk about this one more in the next lecture. For now on, thank you.